Thank you so much, Charles, for the kind introduction and the invitation. Really happy to be here. Having been a grad student here at JQI seminars were a fun part of our Mondays, so it's a privilege to be giving this talk. All right, so as advertised, I'll tell you guys today about atom field interactions in nanoscale quantum optical systems and some ways to engineer them. And more specifically, I'll talk about fluctuation phenomena and non-Markovian dynamics in these systems. Okay. All right. So let me first start with unpacking the title of my talk a little bit. So as we know, atom field interactions or atom-photon interactions more properly are the essential building block of pretty much all of quantum optics, and they play a key role in several applications, ranging from building our quantum computers, quantum metrology, building various quantum devices, simulating our big complex quantum cows with simpler, more controllable quantum cows, and so on. And while all these applications are really exciting and atom-photon interactions are really important, they're also very inefficient. And one way, as we know, to boost these interactions is to shrink our systems down and confine our electromagnetic fields in smaller and smaller mode volumes. And as we do so, this brings us to a emerging, or well, I should say already pretty emerged, family of nanoscale quantum optical systems, which provides both very efficient as well as very tunable and engineerable light matter interactions. Okay, so here what I've drawn are some representative examples. And while these are just some theorist cartoons, of course, these ideas are not just theoretical, they've very much been realized in various labs, including here at JQI. So for example, this picture here was taken from, this one was taken from John Hoffman's thesis here at JQI. In some cases, they've also been realized by the butterfly community. You can see this nice photonic crystal structure in the wing of a morpho butterfly. And not only these ideas are realizable, they're useful as well for building various photonic devices, sensing gravitational fields, building quantum computers, and so on, as we know. Okay, and to describe several of these applications, one can consider a somewhat generic schematic like this, where we have a collection of quantum emitters or atoms that are coupled to each other through waveguides or nanophotonic structures that allowed photons to travel from one emitter to the other. And as in such a scenario, there are two ideal features that one would like to have, among others. One is, of course, to be able to build efficient light matter interfaces. And as we do so, for example, as we try and couple our atoms to the photons in the waveguide, the system also becomes susceptible to the fluctuations of the electromagnetic field, which bring in detrimental effects. Okay, so that's the first part of my talk about fluctuation phenomena. And secondly, we would like to be able to connect multiple emitters over long distances. And this brings into play the memory effects of the intermediary electromagnetic environment, which brings in non-Markovian dynamics into consideration. Okay. All right. So these are the two broader aspects. To explain a little bit more what I mean by fluctuation-induced phenomena in nanoscale quantum optical systems. Here, for example, is a quantum system of interest that could be some atoms or some solid state emitters that are at a few hundreds of nanometers away from the surface of a chip or a waveguide or a resonator. And as these two objects interact via the quantum or also the thermal fluctuations of the electromagnetic field, this interaction results in various fluctuation phenomena like fluctuation forces, loss of energy or dissipation, and decoherence. And these are the aspects that we would like to be able to engineer. And that's what I'll talk about first today. And more specifically, I'll tell you about how one can potentially use collective effects in emitters to modify fluctuation forces. Okay. All right, and in the second part of my talk, I'll discuss non-Markovian effects in collective spontaneous emission between distant atoms. So just to briefly remind ourselves, what do we mean by collective spontaneous emission? So if, say, we have two atomic dipoles that are radiating in phase together, the total spontaneous emission that comes out of the system is collectively enhanced as a result of constructive interference. And this is an effect that's been known since 1954, and we call it as superradiance. Okay, so that's what we know. And one typical example that is made while studying superradiance and collective spontaneous emission is that the atoms are confined in a region that is much smaller than the wavelength of the field that is mediating the interaction. Okay, and if we consider a system where the atoms are really, really far apart, more specifically, let's say the atoms are at a distance that is comparable to the coherence length of the photons mediating the interaction, there are interesting non-Markovian effects that come into play because of retardation. So what we find is that as the photons from one atom reach the other in such a scenario, there's an interesting counterintuitive enhancement beyond the regular superradiance effect, which we refer to as super duper radiance. Okay. All right, so that's the second idea I'll tell you guys about today. So the first part of the talk will be about fluctuation phenomena and collective effects. So we'll be kind of shrinking things down for the first half, and the second half will be about non-Markovian collective spontaneous emission in distant emitters. So we'll be stretching things out there a little bit. All right, so I'll start with the first, some background on fluctuation forces. Fluctuation forces go by several names: London, van der Waals, Casimir, Casimir-Polder, and they're all essentially one and the same thing. So let's say we have two neutral bodies, A and B, that are separated by the vacuum electromagnetic field. And as light-matter interaction happens, there are spontaneous fluctuations in the dipole moments that constitute the two objects, as well as virtual photons in the electromagnetic field that mediate the interaction between the two bodies. Okay, and this results in a fluctuation force, which we call by different names, depending on what's the shape, size, material properties of these objects and who originally happened to study them. So if it's 2 point-like particles, we'll call it London or van der Waals. If it's a gecko climbing on a wall, we call it van der Waals. If it's two perfectly conducting parallel plates, we call it Casimir, or generally two macroscopic bodies. Then we refer to it as Casimir force, and so on. For the purposes of today, I will focus on the situation where we have a particle or a collection of particles close to a macroscopic body, and we'll refer to that as Casimir-Polder interactions. Okay. Now, where do these interactions become important? So, of course, if you walk into a typical quantum optics lab, it looks something like this, which is a jungle of big, bulky optical elements. Well, I mean, that looks like what it is to me as a theorist anyways. So if what we'd ideally like to do is to shrink things down to the size of a chip to make things more modular, for example. And as we do so, we inevitably run into Casimir-Polder interactions or atom surface interactions at nanoscales, which influence how we trap our atoms, how our atoms decay and decohere, and so on. So they're mostly a nuisance that we'd like to control. And to see heuristically what the magnitude of these effects are, one can draw a hand-wavy picture here, for example, of a dipole in front of a mirror at a distance z. And from image theory considerations, we can see that the interaction potential has to scale as 1 over z cubed in the near field limit. And this is not quite the right dimensions. This needs dimensions of energy. And the only energy scale we know in the problem is h bar gamma 0, as far as the interaction between the atom and the vacuum goes. This is still not quite the right dimensions. We need a length scale. And the only length scale that we know in the problem is the transition wavelength of the atomic transition. So we put that in the denominator. And actually, this is not a bad approximation. It's only a factor of 16 away from the Casimir polar potential of a ground state atom in the near field limit from a perfect conductor. Okay. And if we plug in some typical numbers in this expression, we can see that at, for example, distances of tens of nanometers, these forces are strong enough to overpower our typical mechanisms of trapping particles. So what this motivates us to do then is to come up with new ways to better control our particles near surfaces and preserve their coherences. Please.
So in a realistic system where the medium doesn't just have two levels,
right?
Is this K0, is omega naught replaced by some dielectric averaging of the oscillator strengths, something like that?
Great question. So in that case, Casimir forces are not quite additive. So we can reformulate it in terms of polarizability and then replace the atomic polarizability by the medium. Yes. I'll have that later in the talk, so hope it becomes clear then. Okay, so what this then inspires us to do is to come up with ways to control our, atom surface interactions at nanoscales, and to see how one can do that, we can resort to an open quantum systems perspective, something like this, where we have our quantum system of interest that is interacting with the electromagnetic field as the bath or the environment. And the density of modes of the bath is modified by some boundary condition. As the system and the bath interact, there are all these fluctuation phenomena that happen, such as energy shifts or forces, dissipation, and decoherence. And these are the aspects that we'd like to have some control over. So in this picture, one can see how one can modify all the fluctuation phenomena, for example, by modifying our density of modes of the bath using surface optical or material properties or geometry. One can think about modifying the system bath coupling more directly, for example, by using magnetic interactions instead of electric. We can drive the system to some interesting non-equilibrium steady state, which effectively changes the system bath interaction. We can also use correlations internal to the system to, again, change the effective system bath coupling. And while this is not an exhaustive list of the number of things that one can do, this is some ways that we've poked at the problem of trying to engineer fluctuation phenomena in nanoscale quantum systems. And unfortunately, I don't have the time to discuss these different ideas in detail, but I'd be more than happy to talk about them if you're interested later. I do want to mention that there's an interesting experiment that we are collaborating with at the moment in Vienna, where we are looking at drive-induced modifications to the Casimir polar potential between Casimir polar force on a nanosphere close to a membrane. Okay. And for the purposes of now, I'd like to focus on this one idea of collective effects in Casimir polar forces. All right, so as we know, collective effects have been studied in the context of spontaneous emission for a while. And if, let's say, we have n emitters that each emits independently with a rate gamma 0, this emission rate can be enhanced or suppressed by preparing the emitters in a super radiant or a subradiant state. Now, what if we take these collective states and put them near a surface? One can then imagine that the vacuum forces, kind of being the dispersive counterpart of spontaneous emission, there would be a similar analogous effect in vacuum forces as well. So that's the intuition that we start with. And we can draw a toy model to make this intuition more concrete. So let's say, as a toy example, we consider two atoms, a red atom and a blue atom, close to close to a surface interacting with a vacuum electromagnetic field. And we can analyze the system from, again, an open quantum systems perspective, where we consider the atoms to be the system, the electromagnetic field to be the bath, the density of modes of the bath being modified by some boundary condition. And in this picture, we can trace out the bath to arrive at the reduced system dynamics for the atomic subsystem in the form of a master equation, like so. And this master equation now contains all the effects of the environment. And I should also mention that while in the toy example, I just drew 2 atoms, it is definitely possible to extend, the formalism applies to the system of multiple atoms, including drive and correlations and everything. So what this master equation gives us is the reduced atomic subsystem dynamics which is described in terms of a surface modified Hamiltonian that contains the effects of energy shifts and forces, and a Liouvillean which describes the losses on the system in the presence of the surface. Okay. For the purposes of now, since we want to consider collective effects and the forces, we consider the Hamiltonian part, which looks more explicitly like this for the case of 2 atoms. So here we can see that the 2-atom system has these different contributions, where we see that there's an excited state shift and a ground state shift to each of the atoms, of course. And we can understand these shifts as coming from processes like these, where, for example, the ground state shift arises from a process where the atom goes from the ground to the excited state, emitting and reabsorbing a virtual photon. And this process is, of course, energy non-conserving. And the shift is given like that, where the G represents the propagator or the Green's function of the photon going from atom to the surface and back. Okay, and here is the atomic polarizability at a imaginary frequency, which is associated with virtual photon processes. And of course, this can happen at any frequency, so there's a broadband integral. Okay. All right. Similarly, for the excited state, the atom can go down and come back up, which gives us a virtual photon process contribution. And in addition to that, there is a real photon process which can happen, wherein the atom can emit at the resonance frequency ω0 and reabsorb. And this part of the shift, if we compare it with the surface modified spontaneous emission, we can kind of see clearly that the 2 are real and imaginary parts of the same response function. So this quantifies our intuition that we started with, that the Casimir polar shift, or at least the resonant part of the Casimir polar shift, is the dispersive counterpart to spontaneous emission. Okay. All right. And what happens now in the case of the more interesting states, which are the super and subradiant states? So here, for example, we have our collective superradiant state and the subradiant states, which can be written more explicitly like this, where we have a superposition of the blue atom being excited and the red being ground, with the blue atom being ground and the red atom being excited. Now, there can be a virtual process like this, where the 2 atoms can exchange an excitation via scattering a photon off the surface. Okay. And these 2 processes can interfere either constructively or destructively. And depending on that, we can have a positive or a negative contribution to this surface-assisted dipole-dipole interaction term. So what this shows us, therefore, is that there is a dipole-dipole correlation dependent positive or a negative contribution to this orange box. And the coefficient out front here depends on how far the atoms are from the surface. So as a result, we have collective effects, which influence the Casimir-Poulter force of the total atomic system. Okay, we can see this more explicitly when we write the expression for the forces, and indeed we find that for the superradiant state or the subradiant state, there's a positive or a negative contribution from this surface-assisted dipole-dipole term. And this indeed checks out with the corresponding spontaneous emission expression as well. We can calculate this more specifically for an example of two emitters, like we discussed, with some typical numbers. So here, let's say we can look at the force and the spontaneous emission on this system of two emitters as a function of the distance, as a function of the separation between the emitters. And we see that as the emitters get closer and closer together, we get both an enhancement in the total spontaneous emission, as well as a enhancement in the total Casimir attraction. Okay, so this is something that's interesting, but what's even more interesting is that we can consider the subradiant states, in which case we find that there is both a suppression in the total gamma as well as in the Casimir-Poulter attraction. So these states, while having a long lifetime, also have a suppressed undesirable Casimir attraction, which makes them attractive for being able to trap particles near surfaces. Okay. Now, to see how one can possibly observe these effects in the lab, one can consider a solid state system with, for example, emitters embedded in a nanodiamond on a cantilever close to a surface. And if we excite all these emitters in the excited state, let's say if I draw the Dickey ladder, if I excite all my emitters over here, as the system gets de-excited and it goes through the Dickey state, we expect there to be a superradiant burst in the Casimir-Poulter force, just like there's a superradiant burst in the spontaneous emission. And this force burst can possibly be observable for a system of, let's say, 10 to 12 emitters acting cooperatively. So one can get a boost that is as large as 10 femtonewtons for some realistic numbers, I'm told. And this could possibly be measured in the lab as a proof of principle experiment. Okay. Now this brings me to the conclusion of the first part of my talk. So fluctuation forces can be modified by using collective effects, as we see, and this modification can be understood as an interference in the surface-mediated resonant dipole-dipole interaction. We can also see that superradiance in vacuum forces can be potentially used to enhance forces that are otherwise unobservable, and subradiant vacuum forces can potentially be useful for trapping quantum emitters near surfaces with both long lifetimes and reduced decoherence. And as another aspect, actually, this opens a new question about looking at vacuum forces in the presence of boundary conditions that possess correlations. So typically, the standard way we treat Casimir forces is to just treat the boundary conditions as being given. And this opens the question of what happens when those boundaries themselves possess some correlations, for example. Okay. All right.
If I may
please.
comment on that figure, this reminds me of, in some respect, of the Fano line shape scheme, where if you have two atoms, is there a possibility of getting an anomaly associated as the frequency approaches the double excitation threshold?
That's interesting. So I'm not.
Mediated by the surface.
I'm not familiar with the Fano process, but that'd be something good to learn more about. So for the moment, I guess we can discuss that afterwards. Okay. Okay, so while we were working on this problem, actually, there was this very interesting experiment here at Maryland by Pablo Solano, who's a friend. And what what was really interesting here that they saw collective effects in the system of atoms that were close to a nanofiber, as close as 30 nanometers. So this was really exciting. And one of the results here was that if you divide the atomic subcloud into two subclouds, you see that the total superradiance behavior does not change with the separation of the atomic subclouds. And that led to the title of the paper. And this kind of got us thinking, and this led us into another rabbit hole, which I'm going to get into now, where we explore collective emission between atoms at long distances. Okay. All right. So just to start, I'll first define what I mean by non-Markovian dynamics of an open quantum system. So let's say we have our quantum system of interest that is interacting with a bath. When we make the Markov approximation, what it assumes is that the correlations of the bath decay much faster compared to the system relaxation dynamics, such that the system has no memory of its previous dynamics. Okay, so it's a little forgetful system, if you will. And to see this a bit more concretely, to be able to define these timescales, particularly for the scenario that we are interested in, where we have two subsystems that are separated from each other by a distance d, and let's say each of them has a relaxation rate gamma, one can define a system relaxation timescale, tau r, which is 1 over gamma. And let's say the bath excitations have a speed of v. We can therefore define a bath timescale, which is d over v. If we compare these two, if we take the ratio of these two timescales, that allows us to define a dimensionless parameter, which tells us that the system is Markovian when this ratio of the two timescales is much, much smaller than 1. Okay. And this is really interesting because it allows us to see different origins of non-Markovian dynamics. For example, if we have slow bath modes, then we get non-Markovian or memoryful dynamics. If the bath excitations spend more time closer to a system. If we have strong coupling, then again, we have non-Markovian dynamics, or in this case, for example, if we have retardation, we get non-Markovian dynamics. I should mention that collective effects have been studied in the presence of structured reservoirs and slow bath modes. They've also been studied in presence of strong coupling and actually also ultra-strong coupling. And what we are going to discuss here is collective effects in the presence of retardation.
I have a quick question.
Yes.
So the system relaxation gamma,
Yes.
that wouldn't be a function of velocity as well sometimes?
Yes. So this is just a, sorry, this is a bit of a hand-wavy motivation. But I agree. In the proper way of calculating gamma depends on the density of states, which also influences the mode velocity. And so this is a bit heuristic, but I agree with you.
Okay, thanks.
Sure. Okay, and right, and there are several motivations for looking at dynamics of collective dynamics at long distances. Of course, this is relevant to building quantum networks, applications in distributed sensing and metrology. And again, not only these retardation effects are relevant, but they could potentially be useful as well for efficient generation of entanglement. So, for example, it's been shown that one can generate photonic cluster states in the presence of time-delayed feedback, or generate bound states in the continuum between atoms and emitters, atoms and photons distributed over very long distances. Okay, so with that, we write our toy model, which is, let's say, just two atoms coupled to a waveguide, and each of these atoms emits into the waveguide with some rate gamma 1d and emits outside with the rate gamma 3d. Let's say the atoms are separated by distance d, and we prepare them initially in a super or subradiant state. And as the system evolves, we assume that the number of excitations remains preserved as far as the field in the waveguide and the atomic subsystem is concerned. So we can write the state at any given time as shown. And what this, so here you can see, for example, C1 and C2 are the atomic excitation amplitudes for atom 1 and atom 2. Okay. Right, and we can write the we can trace out the field to write the reduced system dynamics of the atomic subsystem, which looks like this, where the first term indicates the spontaneous decay of the individual atoms, and the second term is the time delayed feedback or the retarded back action that each atom sees coming from the other atom. So this term you can see comes in with a delay and some waveguide coupling efficiency and a phase factor that includes the phase of the field that is propagated between the two atoms. Okay, so well, we can solve this coupled delay differential equation system. That's not a problem, and we can understand the solution that we get, which is a series solution, in as a cascade of stimulated emission processes in a hand-wavy way. So what's kind of happening here is that each term comes in every time the atoms see each other. So you can see, for example, when the photons from one atom reach the other, there's a modification to this atomic evolution. And if you look at the time where the atoms first see each other, for example, before they only emit spontaneously, but as soon as they see each other, there's a modification to the exponential decay. And this at this instant, one can see that one can look at the effective instantaneous decay rate. And if you write the gamma at the instant when the atoms first see each other, for the superradiant state, we find that this can exceed 2 gamma, which is interesting. And for the subradiant state, this can be negative, meaning that the information can come back from the bath to the system, making the system essentially non-Markovian. Okay, we can plot this dynamics for an initial superradiant state here, for example. And what we're looking at here is the atomic population on the y-axis as a function of time. And we see that the different curves here are for different separation between the emitters. So if the emitters are perfectly coincident, you want to look at the blue solid curve. And if the emitters are infinitely far apart, that corresponds to the black dotted curve, which is just an exponential decay with a rate gamma, and the blue solid is exponential decay with rate 2 gamma. Somewhere in between, so let's say if you look at the yellow curve, which corresponds to a dimensionless distance of eta equals 0.56, we find that initially the atoms decay independently until they see each other, and then they decay collectively. And when they decay collectively, indeed, we can see on the log scale that this rate is faster than 2 gamma. And this is what we refer to as super duper radiance. And unfortunately, ultra radiance and hyper-radiance were taken by other people. So that's kind of what we are stuck with. And we can also look at the subradiant states. So if we, of course, if we have subradiant emitters that are coincident, they just do not emit, do not evolve. So that's the blue solid line up there. If we have subradiant emitters infinitely far apart, they just decay independently. Somewhere in between, the emitters decay independently, and then they recohere and form a bound state with the photons in the waveguide. So this is a really interesting state, which it's like a giant hybrid molecule of atoms and photons that's kind of delocalized over a macroscopic distance. And This is referred to as the bound state in the continuum, for example, as was pointed in this nice PRL.
I have a question. I may interrupt.
Yes, please.
So when we solve this exact problem, there will be some oscillatory part and some decay part. And actually, in general, it might be actually none of them. If you just consider, so okay, if I just have one emitter coupled to a non-Markovian bath, then the system is neither. It's something that oscillates and then emits. So sometimes one cannot even fit a gamma to it. So
that's correct.
You go back to your equation. How do you actually?
Yeah.
So in like two emitters coupled to a waveguide with a Markovian bath, you would give flip-flop and then the superradiant subradiant decays. And
that is correct.
Yeah.
So I agree that there is no exponential decay behavior anymore. So initially, though, what we can define at most is an instantaneous decay rate. And that's what I'm referring to as a gamma effective, if that makes sense. But I agree that the decay profile, of course, is not just exponential, as we can see here. So there's some modification at the first term itself. And if we go to the higher terms, then there's a even more complicated behavior as the atoms see each other again and again.
I see. And then how is it different between two emitters coupled to a waveguide in a Markovian fashion? Maybe like the difference, it would be more, I wonder how things change basically. When they're far away from each other and you do Markov approximation, and when you don't do Markov approximation, what are the differences?
So that's a good point. Actually, so one thing I did want to point out here, that there's a critical distance of sorts. So I didn't explain why I'm choosing, for example, these two values of eta. It so happens that if your emitters are at a distance below a certain critical distance, they still emit just once, and then there are no like reflections. If it's a distance that's greater than that critical distance, and we can actually understand that critical distance analytically as well from the equations, then the atoms start exhibiting a cavity-like behavior. So that's what you can see here in the blue curve. So if you see the decay first, and then they kind of oscillate. So this is the photonic excitation going back and forth between the atoms, and it's like a cavity kind of made by the atoms for the atoms, if you will. So a bit of a democratic cavity. But to compare with the Markov approximation behavior, the system would never like have any recoherences. So none of these oscillations would actually happen in that case. That's how I would imagine. Like here we could not make the Markov approximation because the information does come back.
Thanks.
Before you go on, I've got another question. This is Phillips. In this model of having two atoms coupled to a waveguide, are you including the effect of a single atom seeing its image in the waveguide, or however you want to think about the waveguide modifies that process?
That is not included. So in a way, that's a good point. So here we are only considering the coupling of atoms, the individual atoms to the waveguide modes that are traveling, but not the near surface kind of interaction, if that's what you're referring to.
Yes.
Okay.
And in principle, that might have an effect. I mean, it certainly does have an effect. The question is, does it have a significant effect on what you're calculating here?
Right. So this is really interesting because the the near surface part is significant, but in a way, what we are assuming is that it's included in the renormalized frequencies of the atoms and whatever the renormalized effective gammas are. So whatever the gamma independent is, or whatever the omega zeros are, all the modifications from the near surface interactions are taken into account in those quantities in an effective way.
Okay.
If that makes sense. And here, I guess the part that we were more interested in was to look at the time delayed, the retardation effect of the atoms on each other.
Yeah.
So that's that's what we are seeing here. But it would be interesting certainly to combine the two together. I agree.
Yeah. Now, one more question. Just looking at this picture here, one of the things that is remarkable about this picture is that there's a kink in the and whenever there's kinks, it's always disturbing. So
right.
Could you comment on that?
Well, yes, I can comment on that. Kinks are disturbing in the sense of there's a discontinuity in the dynamical behavior here, but it is also not disturbing in the sense, okay, I can explain that with my next slide, probably. Let me get there. So the kinks are not disturbing because the system is in fact causal, right? So if I could see, so for example, here in this picture, what we're plotting is the intensity emitted by the atoms as a function of distance and time. And here you can see the two light cones that are being emitted by each atom. So these are the two light cones coming out. And as the field from one atom reaches the other, there's a stronger emission outwards. So that's the super duper radiance part. And here you can maybe agree that kinks are not that bad, because if if the atoms could see each other before they are causally connected, that would be rather disturbing instead.
Okay, well, certainly, it's happy that they're causal, but
right.
It sort of sounds like you're taking a kind of a semi-classical approach where the photon is like a billiard ball, and it takes a certain amount of time to reach the other atom, and in fact, the photon is going to have some kind of a wave packet description, or at least that would be one of the things I would think about, as well as the atom having a wave packet description. And somehow or other, I would expect the kink to be softened.
Right. In this case, let's see, why is the kink not softened? It does get softer with further bounces, I can say that, but it is not soft initially. So if I look at, for example, okay, so or does it actually? So if I look at this case here, there's just one kink, and the dynamics as the system evolves, the field is just traveling back and forth. The atoms kind of form a perfect cavity to preserve the excitation inside. So it just oscillates, and there are no kinks there, if you will. In the other case, like if I have still excitations in the super radiant case, which go between the atomic cavity, in the second run, when the part of the field hits this other atom, that kink is not as drastic as the first one. So they do get softened, but the initial kink is there.
And I think part of the question is, it really a non-analyticity in the population, or is it that at at a well-defined time, it starts to decay much more quickly. Like, so, that there's a rapid onset of something seems expected, that there would be like an actual, undefined point in the first derivative. That seems a little weird, as Bill says. I don't know.
Hang on a
Sorry,
second.
that was Alicia popping up.
So I guess what's coming in here is, well, the instant where the atoms see each other, that could not be before, the this dash dotted line, right? And there is a discontinuity in terms of there suddenly appears a source term, which is driving the atomic dynamics at both ends. So I'm not sure if so I guess the kink to me, or the non-analyticity, the discontinuity is, it's not discontinuous. I should say that it's non-differentiable, and that's okay because of causality in a way, if that makes sense.
I'm wondering whether perhaps the solution to the problem lies in thinking carefully about the preparation. If I were to prepare a system in the excited state, I can't prepare, just from a practical point of view, I can't prepare a system in the excited state instantaneously. I would have to have some sort of a pulse. That pulse would have a certain duration. During the duration of the pulse, there would be some probability that the atom would be excited. And during that time, it could have emitted a photon, and that photon could have gotten to the other atom. I'm just, thinking out loud here.
I think also the atomic separation is not 100% defined, right? They each have some finite size. Yeah. So as soon as you put that in, I would think there shouldn't be a kink anymore.
Yeah. Are these atoms that we're seeing here, are they separated by how many wavelengths of the?
Many.
Are they separated by?
Right. So several wavelengths. I don't remember the exact numbers, but they are separated on the scales of V over gamma, more like. So that's the coherence length of the photon. So that would depend on what's the ratio of gamma to omega 0. So if I have a distance of 1 in the coherence length units, so gamma to omega 0 for optical, like atomic transitions, would be 10 to the 7 or more. Yeah. Yeah, so many wavelengths then. Right. So actually, I agree about the state preparation part, which would bring in, which would probably take care of the unphysical. This is a bit of an idealized situation, right? That we are assuming that the atoms at t equals 0 are prepared in this correlated state, and they start emitting right then and not before. So if we take care of if we take into account the fact that we have to prepare those states in a physical way, I agree that some of these discontinuities might disappear in doing that more carefully. All right. So to go to the next slide. So all this is fun and interesting, but what is this good for, one can ask. And we can define then a parameter, the cooperativity of the system, which is the ratio of the field emitted into the waveguide to the field emitted outside of the waveguide. And what we find is that this cooperativity, which is an important figure of merit for quantum information purposes, unfortunately goes down with delay. So even if the system emits super duper radiantly for some instance, in overall terms, we do not win to improve the cooperativity of the system. But nevertheless, this is something that is to be taken into account when looking at quantum information transfer over long distances. Okay, and we can also look at the effective dipole-dipole interaction in the presence of delay. And what we find is that if you look at the dipole-dipole interaction energy, for example, this is a time-dependent Hamiltonian. So if we look at the instant when the dipoles just see each other, there is an exponential decay here, which suggests that dipole-dipole interactions are not infinite range. So we, kind of answer the question that we started with here. So this is Pablo and his evolution from 2017 to 2020, as you can see. We can also look at experimental systems that already exist, where these numbers are realizable. So we can see some of these experiments, including this experiment in Ido Vox's lab, where we can have etas that are significant. More interestingly, there's an experiment downstairs with nanofibers, 2 nanofiber sections coupled to an atomic cloud, where we are trying to explore some of these effects. And if you have any questions, you should definitely contact Hyokin Arium for the exciting updates on that front. I also want to mention that we are currently working in with a circuit QED platform experiment as well, where we are looking at retardation effects with 2 transmons coupled to a Josephson junction array. And what's nice about the circuit QED platform is that it allows one to slow down the speed of the field by a factor of 100 or so. So with a distance of a couple of centimeters, it's possible to see retardation effects already. Okay, and how much time do I have? 10 minutes? Okay, so I'll just mention this last part because this is something that we recently worked on, and the idea here is to explore, well, similar collective effects in the presence of unequal velocities in different directions. So here, what you're looking at is a system of 2 atoms that are coupled to a waveguide with circulators in between. And these circulators are in turn coupled to waveguides or mediums of different refractive indices or different lengths. And what this effectively allows you to do is to have unequal photon propagation velocities in one direction and the other, right? And this is something that we've been referring to as anisotachy. Aniso means unequal, tachy means velocity in Greek, I guess. So what can happen in such a system is that, let's say, if you prepare our atoms in a collective state to start with, one can have a phase phi L going this way be different for the propagation phase phi R going right. And more specifically, we can consider that the left phase is, let's say, some odd integer multiple of phi, and the right phase is some even integer multiple of phi. So we get destructive interference one way and constructive interference the other way. And this can then, allow for one of the atoms to exhibit subradiant behavior while the other atom exhibits a superradiant behavior. And indeed, that's what we see. So here, for example, you can see in this picture that, that the onset of collective emission is not simultaneous. So the first atom sees the second atom first because the left going field is faster, and then it becomes subradiant. So that's the blue curve. It stops decaying, kind of. And the second atom, when it sees the first atom, it starts emitting faster. So this is interesting because what it shows is that not only collective emission can be not simultaneous, but it can be different depending on the local atom field correlations and phases of the interfering fields with the dipole. Okay, and we can again also see this in terms of the atomic, in terms of the field intensity. here, for example, you can see that the atom 2, the atom 1, sorry, when it sees atom 2, it starts being subradiant and reflects all the field in the other direction. On the other hand, atom 2 is superradiant and super radiates outwards and so on. So this, for example, can be a tool for directional emission, and that's one possible application of such a system, among others. All right, so with that, I would conclude. So like we've seen, collective spontaneous emission can be interestingly modified in the presence of time delayed feedback, and one can have interesting modifications to collective emission beyond Dicke superradiance, and you can also see formation of these bound states in the continuum in such systems. What we also find is that retardation effects lead to limits on dipole-dipole interactions in 1D systems and cooperativity. We can also see non-simultaneous and collective directional emission in the presence of this unequal velocity propagation in waveguides. All right, and going forward, we've been exploring several directions as follow-ups. So how does this affect scale with n atoms, multiple excitations? What happens when we drive the system? How is quantum information transferred in the presence of retardation? And most exciting to me is the experimental demonstrations of these effects. There are also some very interesting papers that have come out in the last couple of years that have already addressed some of these questions. So that's really good. All right, and with that, I'd like to thank you all for your attention, and especially thank my awesome collaborators. So I'm happy to take any questions.
So I had one. This is Zachary Levine.
Mm-hmm.
Yeah. So is the sign? Is it possible to know the sign of the interaction in advance? Is that something you would get from like a Bell state measurement or something?
Sign of the interaction where? Sorry.
Well, you've got the two atoms. Early on in the talk, you've got two atoms, and you're either going to have an enhanced or suppressed decay rate, for example.
Right.
And so is that something that, you just, the atoms are there and you just find out after the fact, or is it something that you prepare, as I say, with a Bell state measurement or something like that?
So the answer in theory is yes, it's possible, but in practice, I am not sure. So in theory, the reason is, so we know, for example, if it's a symmetric state or an antisymmetric state. And secondly, if we know precisely what the phase of propagation of the field is, whether it's an integer multiple of pi or half a pi or so on, then yes, it's possible to predict whether there would be a constructive or destructive interference. On the other hand, it is really hard to know what is precisely the phase of the field that would be when it propagates from one atom to the other, especially for such long distances that we are considering.
Sure. Okay, great. Thank you.
Sure.
Yes. And I'm wondering what's the magnitude of Kanu-Sinha force. So we know that if we believe the one on the Earth surface is like by 1 meter, then the energy shift will be like 16. So what is that for Kanu-Sinha force?
So
could you repeat the question for the online people?
Sure. So the question is, what is the magnitude of the Casimir polar force for atoms near surfaces, I guess, in general? So a heuristic number that I can give you is that at distances of tens of nanometers, let's say for the rubidium 780 transition line, it's about 10 millikelvins, and in energy, and we can convert that to relevant units if. Sure. So it's stronger than mott, for example, like if a mott is at microkelvins or so, I imagine. Yeah.
It can tear atoms out of magnetic traps, let alone optical ones.
I've asked for someone in the rear to, and then we can go. So about the non-Markovian system. So the claim that it's non-Markovian system and it's non-Markovian behavior is first in your calculation you didn't Markovian optimization in the first place, and the second, the resulting behavior is deviating from typical exponential decay. So would there be some kind of attempt to quantify that non-Markovian, for example, looking into the density matrix of the atomic system and just calculating the stability between the two density matrix, how their stability increase or decrease in the process interaction, if you will.
Sure. So the question is there a way to quantify the non-Markovian behavior of the system in the course of the dynamics? And when you say distinguishability, so I didn't quite get that part actually. Can you repeat that?
Just looking at the system dynamics and density matrix, and you put the two orthogonal initial state, and then in Markovian state, you expect they evolve into, in the two initially distinguishable states will evolve into, one more and more indistinguishable over the course of dissipation because the information is taken out of the system. And when you see that initially or at certain point of time, they were indistinguishable, but the distinguishability increased to the system, and then you expected some information from the past as hit the system, and so in that sense, would you be able to quantify?
Yes, I guess so. If I understand correctly, the question is, can we quantify the non-Markovianity in terms of the distinguishability of the system from, let's say, the state to which it relaxes compared to when, in the cases where it's Markovian versus it's non-Markovian. Is that right? Okay. So yes, the answer is actually, those are some of the ways that measures of non-Markovianity are defined. So I've not given a quantitative expression for non-Markovianity here, but it is indeed possible to calculate that. So one way to calculate that would be, for example, at every instant where the system evolves, one can quantify in information theoretic terms how much information is coming in from the back to the system. And if we sum that over the course of evolution, that gives us some non-Markovianity parameter. And you can imagine that would be actually larger for the subradiant case compared to the superradiant case. Now, the other suggestion is to look at how the system differs from, let's say, in terms of its steady state, when you consider Markovian evolution and non-Markovian evolution. That is also a way to quantify non-Markovianity, although that's, so in that case, what you would measure is some sort of a distance from a steady state to which would be independent of memory effects. And if the system is non-Markovian, it would not be in that steady state, but somewhere else, depending on how the intermediate dynamics happened. So that is also a way of measuring non-Markovianity, as far as I know, except that I have not calculated it that way. So yeah.
Did we have a question from online?
Yes, this is Bill again. So now I want to return to the kinds of things that you began your talk with when you talked about how van der Waals and Casimir-Polder and Casimir were all really the same thing. They're manifestations of fluctuations.
Right.
Now I apologize in advance for the fact that maybe this question is philosophical, but when we first encounter the van der Waals force between two atoms, we typically think of it in terms of the fluctuations on the atoms, or at least on one atom, then producing a field that acts on the other atom that produces a field that acts back. And if we look at the interaction between an atom and a surface the way you invited us to, that is, then we think of the surface as providing a boundary condition, and we think of the atom's image. And again, the fluctuations are the fluctuations on the atom. Yes. But when we talk about the forces between two surfaces, we're almost universally asked to think about the fluctuations of the electromagnetic field. But of course, there's no real reason why we should make that shift. We could think about the fluctuations of each segment of each surface interacting with the other one. Now, what my question is, well, first of all, one more thing. It seems like we dare not take into account both the fluctuations of the field and of the atoms. So what I want you to do is to tell me about that. It just seems it seems like an interesting situation. So I want your perspective on it.
Yes, first, thanks for the question, because it's a great question. And in fact, you can notice there are little dipoles that I did make in the surface here. So I personally am in favor of the democratic way of assigning fluctuations, which is to both the matter and the field degrees of freedom. When you, in mathematical terms, what it kind of boils down is how you order your operators. If you normal order them or if you anti-normal order them, that pertains to assigning your spontaneous fluctuations to the matter degree of freedom or to the field degrees of freedom. You can order your operators symmetrically as well, which ascribes spontaneous fluctuations to both matter and field degrees of freedom.
Okay, so this sounds reminiscent of the idea of ascribing spontaneous emission to field fluctuations or radiation reaction.
Correct. Yes, yes. It is precisely, it has the same origin.
Okay, so so I think I've got the idea. You could do either one, but you prefer to do both.
Well, it depends on the situation. I personally prefer both as much as one can, but you can imagine that, if it's two macroscopic bodies, it's harder to keep track of like all the little degrees of freedom. So then it's better to just talk in terms of what effective boundary condition that is there for the field, and then think in terms of field fluctuations. So I guess it's I would rather do it democratically, but it's a matter of convenience at the end.
Right. So it's so convenient when you just have surfaces to think only of the fields. That you sometimes see people say that the existence of a Casimir force between two surfaces is proof that the electromagnetic field is quantized and therefore has quantum fluctuations. But of course, it sounds like from what you're saying, it's nothing of the sort.
Right. Yes. So I agree with that. In fact, actually, the way Casimir-Polder forces were discovered first, it was in the other picture, which is that they were trying to explain the stability of colloids, and particularly why some colloids are such that so the situation was the following. So let's say you have a colloid with some particles that are at a typical distance, which would create a van der Waals force, which goes as 1 over z to the 6 or 1 over r to the 6. And if you do not take into account retardation effects, then these colloidal forces would be strong enough that the particles would just clump together. But if you take into account retardation effects, then you get a 1 over r to the 7 force. And that explains, okay, the forces are weak enough, these particles shouldn't clump together, everything is stable. So that's how the forces originated. And then after they did this work, then Casimir had this idea of two parallel plates and Casimir forces. So that came afterwards. But the origin is in the particles having fluctuations picture.
Yeah. Okay. Thanks.
Sure.